Hello everyone and welcome. My name is Eric Coleman with IIST and I will be the moderator for today's webinar, Defect Prevention, a Tester's Role in the Process Improvement by Mike Ennis. We're excited you're able to join us today and set aside an hour to attend this webinar. This webinar is one in a series of free webinars to introduce the topics as well as the presenters of the upcoming SQTM conference in San Diego, California, September 13th through the 18th at the Sheraton San Diego Hotel and Marina. The conference focuses on advancing the test management and quality management professions by providing practical methods based on best practices. The ongoing theme of the conference, Practical, Proven, Feasible, keeps the focus on what works. To view the conference program and more information, visit www.qualitymanagementconference.com. Be sure to join us for the next webinar in the series, Improve Lifecycle SQA with Measurements by Al Sorkowitz on April 15th from 11 a.m. to 12 p.m. Central Standard Time. To learn more about this and other webinars in the series, go to www.qualitymanagementconference.com. This webinar is being recorded and will be made available for viewing within 48 hours at www.qualitymanagementconference.com. I will now turn the webinar over to today's presenter, Mike Ennis. Mike?
Thank you, Eric. Good afternoon, folks. It is a pleasure once again to talk to you about defect prevention and testing and quality assurance. As we look at our webinar agenda, this is just a highlight of what would be presented during the full day course at the upcoming conference. So today we're going to talk about what is defect prevention and why is it so important. We'll talk about quality assurance versus quality control. We'll dive into, at a high level, talk about some defect prevention techniques. We'll get into some defect detection techniques, just an overview, and then we will wrap up really talking about understanding some of the key metrics that drive process improvement and therefore would also help drive defect prevention. As Eric mentioned, if you have questions, you can use the hand signal. You can use your boxes to write out questions, and we'll save those questions towards the end, and hopefully I'll be able to get through all of them. So let's talk about defect prevention versus defect detection. Want to lay the groundwork in terms of understanding what those terms mean. When you think about defect prevention, these are the testing techniques that are in place to prevent defects before the artifact has been developed or before the actual phase of the project has occurred. The goal is to prevent defects. Defect detection, these are testing techniques that are designed, these are your more formal testing techniques to find defects after the artifact has been developed, or really at the start of your formal test phases. We'll talk more about the differences between the two as we go through several slides. You can see this slide here, why defect management or defect prevention is so important. If you look at the amount of money that it takes in order to fix a defect, the further down the SDLC. So let's take an example of you find the defect in the analyze phase, which means that it's typically a requirements-related defect. If you find that defect within that phase, the cost to fix it is pretty minimal. It's really the amount that it took you to create it. But to find that same defect, let's say in design, you're typically going to pay twice the amount of money or twice the amount of resources to fix it once that defect leaks to design versus 4 times when it leaks to build. If you don't find that defect until you get to your formal testing phase, the typical cost is going to be 10 times the original cost of that defect. And then deployment or rollout maybe 60 times, and then if a customer finds that same defect, the typical cost is really 100 times to 300 times plus, and sometimes even more than had you caught that same defect during the original phase in which it was introduced. Another reason why defect prevention is so important is companies are trying to do things faster for less money. And the companies that understand best practices, they know that in order to find the quickest way to find a defect, or the quickest way to, I would say, roll out a particular project, is you want to find defects as early as possible. So you may have heard of a shift left methodology. That's really kind of what we're talking about, defect prevention. It's shift left. We're moving quality left, to the left of the test phase. Companies understand that if you wait until your formal testing phases in order to find a defect, yes, that's better than how we've done it over the past couple of decades, but it's still costing the company a lot of money to do that. So they want to find those defects earlier and earlier in the software development life cycle. And from a testing perspective, we play a very important role in identifying those things, because based on our involvement, based on our attention to detail, based on our ability to review documentation and to look for consistency and standardization, there are a lot of great things that we can do in some of those earlier phases that would help with the identification of defects early, as well as facilitating a more efficient testing cycle once we get into those phases. Let's talk a little bit about stage containment. And what this slide represents, in a typical IT organization, you can see you've got two terms here. One, the top column is called defect origin, and the bottom is called defect discovery. Defect origin, so this is going to be the phase of the project that the defect originated in or was injected in. So this was the first place that the defect got into the actual application. Defect discovery means, so this is the phase of the project where we actually found the defect, and there's a difference between the two. There's a difference between where it originated or where it was injected versus where we found it. Based on industry standards, and this data goes back several decades, 40 to 60% of all defects originate in requirements and design. 20 to 40% originate during coding or assembly test. Some people might be surprised by those figures. Actually, you shouldn't be. Requirements have been known to be the culprit or the villain in terms of where the majority of defects still reside, because companies still have not mastered how to write good quality requirements. Either they're moving too fast, either they're not as engaged with the business at that time, or maybe they're using a methodology where when the requirements were first defined, the requirements change over time. So the application really wasn't able to catch up with the requirements, and you wind up finding issues later in the software development cycle. But 40 to 60% of all defects originate during the requirements and design. And normally, if the requirements are ambiguous or leave a lot to be desired, then our developers take liberties in terms of how it's designed. A lot of this is due to not having the adequate standards in place, reviews in place from a development perspective. So the quality gets shifted to the right, and we wound up finding it in the later testing phases, which is illustrated here. This is pretty typical. So going back to the previous slide, or the previous notion that 40 to 60% of defects originate in requirements and design, and you can see the stage containment it's a lack of stage containment, because we're not finding 40 to 60% until we get into product test and maintenance. You see those lines are almost horizontal. That's not very good stage containment. Stage containment is going to be when you find the defect either in the exact same phase that it originated in or just one after that. So those lines going from origin to discovery should be almost vertical in nature if you have good stage containment and if you are employing very good defect prevention techniques. So if we look at some of these percentages, I'll just reiterate. We talked about the majority of defects originate 40 to 60% requirements and design, 20 to 40% originate in coding with coding issues and assembly tests. But you look at on the bottom where we discover them. So even though 40 to 60% are originated in those earlier phases, we're finding 40 to 60% within the later, more formal testing phases. And going back to really the first slide that we talked about, the actual cost. So when you find that defect in assembly, product test, and maintenance and above, the cost to actually fix that same defect now is going to be 100 times X of what it would have cost if you had found that defect within the same phase or one right after. Let's get into quality assurance versus quality control. And apologize for, I will be abbreviating some things, just providing an overview in order to strip this down for the actual webinar. There is a distinction between quality assurance and quality control. Let me start with that. Quality assurance, these are normally your activities that govern how testing is going to be, or quality is going to be measured throughout the SDLC. It expands beyond the testing team. It expands beyond the development team. It's analyzing the entire life cycle in all of the teams that are involved in that. Quality assurance sets the guidelines. They define the guidelines. They measure the effectiveness. They measure the reporting. They do the analysis to understand why this particular application has more quality issues than application B. So they do those analytics. Quality control, on the other hand, is going to be very, very specific to the application that's being tested. These are normally two different groups. Depending on your organization, unfortunately, sometimes quality assurance and quality control are the same people, which makes it a little bit more difficult to manage. But as organizations get more and more mature, they get larger and broader, they tend to differentiate the responsibilities between the quality assurance group versus the quality control group. If we look at this graphic that we've got right now, this is a great illustration. I don't want to say great since I created it. It's a good illustration in terms of how quality assurance and how quality control work together within the SDLC. So the way we read this, and hopefully it's not confusing to you, you can see that we've got quality assurance activities in red, we've got quality control activities in blue, and then we've got, from a development perspective, those activities along the horizontal SDLC in black. So let's walk through this very quickly. You can see that you start with requirements, so that's normally in the analyze phase. So what's happening here? So requirements are being developed and vetted by teams. The quality control group should be involved during that period doing some requirements analysis. The quality assurance team or the process should facilitate that review, and there should be a sign-off of those requirements, that they have been vetted, that they meet all of the criteria from those groups. And as you move into design, functional specs and design specs are being created by the development team, the quality control team, or the test team. At that point, are creating the overall test strategy, project plan, test plan, test plans are being created during that period. From a quality assurance perspective, that process is ensuring that the project plans, test plans, and strategies are being reviewed and signed off. As you go into your design, design specifications are being created from a development perspective, from a quality control. The test team might be undergoing training on specific test tools or the technology that's going to be tested. Test cases are being created at that point. There's also a review sign-off from a QA perspective in terms of ensuring that all of the right stakeholders are reviewing those artifacts. As you move into additional development perspectives, you might have a proof of concept, or they might go into the build phase. You can see the documentation and code is being created during that period. From a QC perspective, the environment might be getting set up at that point. You might start some automation as well. You might start some test scripting, which is the difference between test case creation. Again, from a QA perspective, you've got inspections, reviews, and sign-offs going on with those artifacts during that period. As you go into code complete, and I mentioned you might be starting some automation as well, as development moves to code complete, then the ownership of the project really shifts to quality control. So now you can see we start our test case execution, and then there's the cycle of defect resolution going back and forth with development. Now you might have several test cycles within that period, or you may just have just one, but there is defect resolution in between there. From a QA perspective, the project is under intense change control. So now you've got your defect management that's taking place, whether it's an enhancement, an issue, or a defect. Things are being resolved. Everything is being documented. As you go into deployment and implementation, you can see that there are end-user reviews taking place. You might be doing some user acceptance testing as you move into cutover activities. From a QA perspective, you're going to wrap up the project with typically a QA summary report or some type of archiving of the system. You may have a handover of the artifacts to the maintenance team, etc. So in this slide, you can clearly see how those three entities work in parallel with each other as they move through the SDLC. More specifically, you can see the function or the role of quality assurance as your traditional test and development teams go through the standard activities that they would walk through in a project life cycle. Let's move into I'll talk briefly, just provide an overview of some defect prevention techniques. In the course, we would really look at 4 techniques that testers can and should be involved in from a defect prevention perspective. These activities are all occurring before the formal test phase. These activities are occurring in your analyze, design, and build phases of the project. The first technique that we would talk about is going to be your risk-based testing. The second, third, and fourth are kind of in the same family. These are your inspections, reviews, and walkthroughs. As we look at risk-based testing, interesting stuff here, because if you ask 10 people what is your definition of risk-based testing, you might get 10 different answers. And that's because as the tester, we all probably do some form of risk-based testing, whether it is a formal process or some type of informal mental model that we use. Well, the risk-based testing analysis that I'm going to talk about is really, I want to call it risk-based testing on steroids. because what it's doing several things. It's going to be, one, looking at your requirements, and this is at the requirement level that we're doing this analysis. And I'll talk about the factors that we're going to be looking at. There's 4 key factors that are going to contribute to your overall, and I'm going to say your risk, your overall risk score. And I know we're in a webinar, so I'm just giving you a high-level overview of what that is and what those factors are. The full-day class would definitely get into what type of templates that you would use and how you would use this through the SDLC. Let's talk about these factors. The first one is going to be your impact, which would be similar to severity. So as a tester, we should be very familiar with understanding we find the problem and we have to know what's the severity of the defect. Well, here we're looking at the requirement, and we're understanding the impact if we do not implement this requirement properly to the end user. Let me back up a second. One of the most important factors in terms of doing this analysis is this isn't the tester doing this analysis alone. This isn't the developer doing this analysis alone. This isn't the business doing this analysis alone. This analysis needs to take place from a project perspective. So you would have the project team together evaluating each requirement based on these factors. Now, obviously, you could do this in isolation, and then you could bring the results back together as a team so that you can review how each group designated this particular risk. But the key point I'm trying to emphasize here is this process or methodology is not used to be done in isolation, meaning I would not expect that a tester would fully be able to articulate and understand what is going to be the impact of if this particular requirement is not implemented properly into development, not to development, into production for our customers. So you would give it a scale of 1 to 5, and you would rate the impact of this requirement as it gets deployed to production. So a 5 is going to be critical, so that if we don't implement this requirement correctly, the impact is going to be tremendous. That's what a 5 is. So you would use a scale of 5 to 1. Now, a 5 could also be, if we don't implement this requirement, 80 to 100% of our customers are going to be affected by it. So you could do it that way. And then a 2 might be 60 to 70, a 3 might be 40 to 50, et cetera, et cetera. The next factor is going to be probability. This is an assessment of the likelihood of an error of delivering this requirement into the production environment. So this is normally coming from development. They've got to gauge their comfortability with being able to code this particular requirement effectively in development and then pushing it to production. Again, a 5 is going to be very likely. A 1 is going to be unlikely. So a 5 is going to be the worst, meaning it's very likely that the likelihood of an error being delivered into production. This might have something to do with the level of complexity that it's going to take in order to develop this particular requirement. That could be a factor that might be used. It could be other factors. It could be the number of people or the number of interfaces that are involved to do that. Might be on a more complex end. The third factor is going to be your level of control. Again, this is probably a good development factor here. How much control does the development team have over the implementation of this particular requirement? So Think of it in this way. In order to implement this requirement, the development team maybe has to touch one module, one interface. That's pretty low. That's pretty low. So you might give that probably a 1 or 2. But in order to implement this particular requirement, you might have to touch 10 different modules, 20 different interfaces. That's going to be a 5. You might have some aspects of code that are done by a third party, etc. So you would give a level of control on a scale of 1 to 5 as well. The last factor here is going to be your confidence levels. This is really where a tester can come in. So this is a rating of the tester's ability to understand the clarity on requirements and give a level of confidence that we have everything that we need in order to test this particular requirement. And I actually may have the numbers turned around here. Indicates the confidence level of the risk evaluated. So I would say a 5 should be very low confidence, and then a 1 should be very high confidence. So this is, you've looked at the requirements, so you've looked at the testability of the requirement. Does the requirement have all of the information that you need in order to adequately test this requirement? Do you have all of the data that you need in order to test this requirement? Do you have the right environment in order to fully test this requirement? So this is your gauge in terms of how well or how effective do you think from a testing perspective we can test this particular requirement. So those are, you could have more factors, but these are the 4 key factors. So you would take the, I don't want to say the average, but it might be the average of these 4 factors, and this is going to give you a risk factor. And you're going to do this at the requirement level as well as at the overall project level. So each requirement will have its own risk factor, and it will total up the overall risk rating for that particular application. And you would do this at the beginning of, or you would do this at the end of analyze. You would do this at the end of design, and you could also do this at the end of build. The reason why we're doing it more than once is because risk changes. If we evaluate the same requirement at the end of analyze, the same requirement at the end of build, more than likely one of these factors will have changed. And during the full day session, we would go through some of the factors that change these things. But the point being, risk changes over time. The risk should go down, meaning you might not know much about that requirement at the very beginning because developers haven't done the full analysis, etc. So your risk rating for this particular requirement, let's say if we were just using the 5s, and we counted up to 5, so let's say a 20. So when you did this the first time, your risk rating might be 20, meaning 5, 5, 5, 5, the highest risk available possible for this particular requirement. Well, if you did the risk assessment at the end of design, it might go down to 15. So now you see the risk is lowering as you are getting into your testing phases. That's the reason why we want to do this more than once. Or that risk could be going up, which should be an indication at the project level that something's going on with this particular requirement. I found this methodology to be extremely effective in terms of driving risk-based testing, because obviously this is going to highlight the requirements that have the highest amount of risk, and really should be the focus of where your testing should be. So the output of this exercise should be driving your testing priorities, because if you have requirements that on average, let's say, using that scale of 0 to 20, if you have 80% of your requirements that have a risk rating of, let's say, 15 to 20, those are the requirements that you should be testing first because they have the highest risk. So not only should it be driving your testing priority, but should it also be driving your development priorities? Because you're all looking at these requirements and you're all doing this analysis together. So development should also be looking to pull that risk forward and try to understand some of these requirements a little bit better as well. So that should drive their development of code as well. It's extremely effective in terms of pulling risk forward, understanding what the key risks are going to be, driving your testing priorities, identifying risks early, etc. And as I mentioned during the one-day class, we will have exercises and really get into understanding how to do an effective risk analysis. I'm going to talk to the other three at once. So this is basically, these are your walkthroughs, reviews, and inspections. And the reason why you have three different types is depending on what you are reviewing, you're going to use one of these techniques. Excuse me. For a test plan or test strategy, you might do a walkthrough, which is really a high-level, pretty much informal presentation of your overall strategy. You wouldn't necessarily give another team a 100-page test strategy. You might want to take the high points out of that test strategy into a PowerPoint and do a very high-level walkthrough emphasizing the key aspects of what you're going to test. If you were doing a code review or an inspection of a design or technical specification, these are more formal techniques where you are documenting results. You might have an inspector, you might have a moderator. It's a formal review process where you're taking notes, documenting the results, etc. in terms of how that team needs to accomplish these things. Very important that that testers become a part of those activities, because for several reasons. One, it gets us involved early so that we can understand, at least we can understand the application and the architecture that we are about to test. So if we don't find any defects whatsoever, it should at least give us a better knowledge or understanding of the application, which should help us test better. We can also, testers have or should be detail-oriented, so we normally find inconsistencies, incorrect information, ambiguity. All of those are attributes that a good tester brings to bear and can add to those activities to find defects. Now, every issue that you find, every anomaly that you find, every ambiguity that you find is a defect. So these are defect preventative activities. Let's get into static testing. So there are two types of static testing techniques that we want to talk to briefly. We just went through talking about the manual static techniques. So static means not moving. So these are all of your activities that are happening during analyze, design, and build. You don't have the application yet. So these are all let's say white box, or really a white box activity, or a verification activity, because we're getting into verification versus validation. So risk-based testing, inspections, walkthroughs, those are all your static techniques. They're also automated techniques. So there are tools that development can use that can do the analysis of code. The application is not running, but it is doing an analysis and it's checking errors for, it's checking areas for complexity, duplication, ambiguity, dead code. There are lots of great tools that are available in the industry that developers can use that can identify serious issues within their code even before they compile it. even before you start running it as an application, which is also a good defect preventative method, because if it's identifying complexity, let's take that for an example. The more complex a module is, the more difficult it's going to be to develop, the more difficult it's going to be to test, the more difficult it's going to be to isolate what the issue is if you find a problem. So let's say you run your static analysis tool and it identifies several modules that have a high threshold of complexity. Well, now that developer has the information presented to them that, you know what, they can reduce the complexity of that particular module. They can break that module up into 2 or 3 modules. Now they have the data in order to be able to do that they did not have before. Once again, this is a defect preventative method that from a testing team, you can bring that to your various applications or various project teams. Some things, additional things that the static analysis tool generates: call trees, hierarchies, structure charts, and it's evaluating your complexity, your conformance, your consistency, risk, so we can identify security holes, etc. Lots of great things that a static analysis tool can do that. During the class, we'll talk about what some of these tools are so that you can do some research. Usually we may also have a vendor available at the conference where you can actually take a look at some of the vendors that specialize in this. Just briefly, some benefits. Discovers, these are actually benefits to the manual techniques as well. Purpose is you're able to now discover defects and errors prior to your formal testing activities. You can identify defects that might not be easy to find in dynamic testing. You're identifying dependencies, inconsistencies, etc. As we move into defect detection, there are a couple of different types of detection techniques. You've got functional, you've got structural. We'll talk briefly about verification and validation, understanding how that fits into the V model. Basically, everything that we've been talking about so far has been verification. We haven't started testing anything. Validation is usually our more functional, our more formal black box testing techniques. So the verification techniques are your walkthroughs, reviews, inspections. From a validation perspective, now you're getting into your test cases, scripting. There's some white box. We do talk about a few black box testing techniques in the class. We'll talk about equivalence partitioning, boundary value analysis, as well as experience-based testing. These are 3 of the more common black box testing techniques from a functional perspective. So we will dive into what those techniques are and how you can add that to your repertoire from a particular testing perspective. And then we get into process improvement. And when we think about process improvement, there are several key metrics, and I'm very keen on metrics being a good tool to understand areas for process improvement, not only in the development process, but also in the testing process. So I've identified really 6 key metrics that can be monitored that really pull out process improvement. And once again, the purpose is to leverage this information in order to reduce defects either in future test phases or in future releases. So let's say the first metric that I'm going to collect is defect discovery phase. So this goes back to really the first couple of slides where we were looking at the phase in which we found the defect or discovered the defect. Usually that's going to be in your testing phases, whether it's product test, end-to-end test, component assembly, UAT, etc. The next metric I'm going to look at is my discovery method. How did I find the defect? Very, very important. What technique did I use in order to find that defect? Was it a positive test case? Was it a negative test case? Was I using equivalence partitioning, boundary value analysis? Was the developer just doing some investigative or guerrilla testing? Did I find it using a manual script, or did I find it using an automated script? And we'll get into some of these metrics in the next few slides. Defect origination phase, going back to at the beginning of the webinar. What phase did the defect first get injected or originate in? Understanding that. What phase did the defect first get introduced into the application? The next, probably the most important, root cause. Primary reason why the defect occurred. What was the reason for that defect? Was it a requirements issue? Was it a design issue? Was it a coding issue? Was it a testing issue? So how can testing cause a defect? Well, the tester could have executed the script incorrectly. It could have been an environment issue that caused the defect. It could have been a data issue that caused the defect. Now, I'm not saying that the tester caused it, but these are things that occur in the testing phase. Did the tester misinterpret the results of the test? So there are a handful of ways in which the root cause can actually be testing. Defect resolution type. So how did the defect get resolved? Was it really a defect, or was it a rejected defect? Was it a duplicate? There are several reasons, and we'll get into some of these as we go through some of the metrics so that you can understand how you can use this for process improvement. And 6, the defect leakage reason. So this is the reason why the test team, our team, did not find a particular defect when we should have found it. So now let's get into some test phases. So let's say, I'll make it easy. The example I want to use is your UAT testing. Normally this is done by the business. Normally this is not done by the testing team. Let's say that your UAT business finds, let's say, 10 severity 1 defects. So from a testing perspective, I need to understand why my team, why we didn't find those 10 defects. There might be legitimate reasons. So we want to understand what is the reason why that defect leaked to a stage or phase beyond the one that it should have been caught in. Why did the customer find this defect and we didn't find it? Why did we find a defect in our end-to-end testing that we didn't find in unit testing or integration testing or assembly testing? So let's get into some of these defects, and you can see how we use them. I'll just try to provide a brief overview of some. So this is, we have gathered all of the defects by discovery phase. So if we look at some of this data here, basically we see that 82% of the defects were found in testing. We can see that 8% were found in build, probably as a result of their unit testing. We can see that 4% were found in design, 5% found in production, and 1% in analyze. This is pretty typical because we are relying on the testing phase to find the majority of defects, but this is not from a best practice perspective. So if I were to look at these metrics, First of all, I would say that the 82% that's put too much pressure on the test team to find all the defects. There should have been a higher percentage of defects found earlier in the software development cycle, specifically in analyze, design, and build. Remember, let's go back to the first couple of slides. 40 to 60% of defects originate in analyze and design, but we found a total of 5% of the defects were actually found in those, based on this data, actually found in those phases. We've got to do a better job of identifying and reporting defects in those earlier phases. The build phase, 8%. There should be more defects that should have been found in that phase before it went into the formal testing phase. Now, one of the things that I did on this particular graph is I've got testing looped into one big bucket, where actually I could break this out by assembly, by unit, by end-to-end, as well as UAT. We'll do that in the class. And then we got the 5% that were found in production. So we definitely, 5% is a little high. Industry best standards are about 1 to 2% of defects get leaked to production. So you can see that 5% is above that threshold. We want to understand what those issues are, as well as how the customers found these issues, and we weren't able to find them in testing. And actually, you can actually see where I've broken out the testing phases. So this is using some of the same data. You can see that from left to right, we found, 15% in unit tests, component tests. We found 50% in integration testing. We found 25% end-to-end, and we found 10% in user acceptance testing. It's not bad, but we want to understand, were they defects that were found in integration testing that should have been caught in component? We also want to find, were there defects found in end-to-end testing that should have been found in integration? More importantly, if you're looking at this data, my UAT users found 200 defects. That's a lot of defects. So I need to understand, one, the severity of those defects, as well as why did my testing team not find these defects in either the system or the integration testing cycles. Again, process improvement, defect prevention. The purpose is to prevent defects from being found later in the cycle. So even as a tester, our job is to prevent defects. I don't want defects to go beyond my test phase. Let's look at defects by discovery method. So now we can see, let's look at the data. So we've got 50% that's been discovered by a manual testing method. We've got 11% that was found by an automated testing, by an automated test script. We've got 4% found by use cases or unit test cases, and we have 21% that were found by a developer who was testing during QA, and then we have 15% that have none. Let's talk about this quickly. I know we've got about 10 minutes left. One, let's see what I want to talk about first. Let's talk about the automation. Let's talk about the automation testing. So I found 11% of my defects in automation. Now, one of the examples that I use, let's say you've got an automated test team, and let's say that you are spending, let's say it costs you $2 million a year to fund this team, and you were able to see that for this particular project, your automated test scripts only found 11% of the defects. Is that good or bad? Now, I'm just using that as an example. Is that an acceptable return on investment for you spending, you're a test manager, you're spending $2 million a year on your automated testing team? Is that an acceptable return on investment for your automated scripts? It could be yes, it could be no. It could be, what's the focus of your automation? If your automation is strictly to focus on regression testing, that might be okay. But if your automated testing is supposed to be doing new automation while the application is still being developed, then you would want your automated test scripts to find more defects than that. Let's look at the developer testing. So now this is a developer who is doing testing after they've turned the code over to you. So they found 200 defects, or 21%. I would want to understand what type of testing that developer was doing, one, that my team wasn't doing. Secondly, I would want to understand why this developer didn't find it in his unit testing, where he should have been doing all of that testing. Did something change? I would want to understand why those, what methods that he's using. Maybe I need to teach my testing team some of those methods. And then the last data point I want to talk about on this is the 15% that are none. So how does this happen? Well, this happens when you're using a defect management tool and you've allowed this field, which is, you might call it defect discovery or test method, you've allowed that field to be an optional field. So it was an optional field. So when the tester found the defect, they didn't put a value in. So the value was none. So this is an example of bad quality. So as a test manager, I've got to ensure the quality of my defect management tool, because now I've gone through a release and I've basically got about 15% of defects that I don't know what method was used in order to find the defect. Now, to you it might not be a big deal, who cares? But from a testing perspective, this is a very important metric for me, because it helps me evaluate the quality of the testing that my team is doing. It helps me evaluate the quality of the techniques that they're using. If my team is using techniques that are ineffective, then I either need to get rid of that testing technique or revise that testing technique so that it is more effective. During the class, we'll talk a little bit more about what some of those things are. I want to move quickly along. Do want to save a few minutes for some questions. So, sorry, it's a lot of data that I've tried to comb through in an hour. This is basically looking at the origination phase, similar to one of the first couple of slides we saw in the webinar. So you can see that 42% of these defects originated in the build cycle, 19% in test, 3% in production, 20% none, 9% analyze, excuse me, 7% design. So the first thing I'm going to look at that is pretty big is the 42% in build. That's a lot of defects that originated in the build cycle. So these are usually coding issues. So what's the issue with coding? So your development manager might be very interested in this. Are they using coding standards? Are they doing code reviews and peer reviews and things like that? Because that's a lot of defects that are originating pretty much due to bad code. There was an error in the code. Secondly, I want to look at testing. 20% that originated in testing kind of goes back to what I said a few minutes ago. What's the nature of these tests? Were they tester error? Were they environment issues? Were they data issues, script issues? I want to understand what that is. Last thing I want to note on this slide is the none. Once again, we have left that field, the defect origination field, empty. So the person did not put a value in. So now we have about 20% defects where I don't know the origination phase. I can still get it from another metric, but that's a problem because I can't do any analysis on that 20% because they didn't fill it out. Let's see. This is the defect by resolution. So this is how the defect was resolved. You can see the 63%, it was a real defect. I'll just talk about the 13% as designed. So as designed means that we found a defect, but it was rejected because the developer said the application is working as designed. From a testing perspective, I need to understand why my tester thought that that was a defect in the first place. Is the requirement out of date? Is the application wrong? There's got to be some disconnect between the documentation as well as the application that caused my tester to think that this was a defect in the first place. And then you have duplicates and not responsible. We want to understand, what those percentages are, etc. With that, that's really all I wanted to cover in today's webinar. I know it was a lot of information. I encourage you guys to attend the conference in San Diego and really learn more about what some of those techniques are. And we can spend definitely more time drilling into the metrics and the techniques, etc. I will go to some questions now. See a question, how can a defect originate in the testing phase? I think I may have answered that. Tester could have executed the script wrong. He could have interpreted the information wrong from the testing, from the results. It could have been a test data issue. It could have been a test environment issue. It could have been a configuration issue. All of these things originate in the test phase. That doesn't mean that it was caused by the tester. Good question, Joshua. How does this look in an Agile methodology? It looks the same. Agile, you're just doing these cycles. You're just doing these cycles sooner. You're doing these cycles more times. So you're still looking at the same metrics that are a part of that sprint or that iteration. The same thing applies. I think there was a question on how can you use automation for unit testing end-to-end. Well, you can absolutely use automation for your unit testing. Developers can use automated test cases, JUnit, things like that. Your end-to-end testing, definitely you can use automated testing for your regression suite, etc. Another question about how can you apply this to Agile. This is based on waterfall, but Agile is nothing but a series of waterfalls back to back. So you can use the same methodology as you go from iteration to iteration. Very good question. This process would not slow down the Agile process. You should always be tracking metrics in the effectiveness of your testing. What is the typical product life cycle? I found test cycle is constantly being shortened. Yes, that's why we have to do more things like risk-based testing and defect prevention, because test cycles are being shortened. The goal is to find defects before it gets into testing so that your test cycles can be shorter. Is eliminating manual testing of the application a good way to improve the quality of the application? No, you should always want to do some level of manual testing. You definitely want to automate as much as possible so that your test leads can really focus on exploratory testing, guerrilla testing, and figuring out the funky ways that our customers can use our applications. Do security defects require a different methodology of testing? No, they do not. Normally in security, you would be executing your functional testing by a particular security role. So you might have someone as a user administrator. You might have someone as an end user, and they would have different roles associated with them. Can you suggest a static testing tool? McCabe Metrics, MCCABE, McCabe Metrics. And with that, I believe we're at the top of the hour. I want to thank all the folks. Very good questions. Thank all the folks for attending and staying on for the entire time. Look forward to seeing you in San Diego. Thanks a lot.
Thank you, Mike, for your time today, and thank you to everyone for joining us for today's webinar sponsored by IIST, the leaders in education-based certifications and training. For more information on how IIST can help you or your organization, please visit www.iist.org. You can follow IIST on Facebook, Twitter, LinkedIn, and YouTube to find out more about IIST news, events, and promotions. Thank you all again for joining us today, and have a great day.